Welcome to this coding tutorial. In this session, we'll be tackling LeetCode problem number 121, best time to buy and sell stock. This is a classic problem that tests your ability to identify optimal strategies for maximizing profit while navigating constraints. Stay tuned as we break it down step by step and explore various approaches to solving it. In this problem, we are tasked with determining the best time to buy and sell a stock in order to maximize profit. You are provided with an array called prices, where each element represents the stock price on a specific day. The goal is to choose one day to buy the stock and a later day to sell it, ensuring that you adhere to the rule that selling must happen after buying. The objective is to calculate the maximum profit possible from this single transaction, and if no profit can be made, you should return 0. The input is a list of integers representing stock prices, and the output is a single integer that represents the maximum profit achievable. Now, let's look at some examples to understand the problem better. Consider the first example, where we have prices equals 7, 1, 5, 3, 6, 4. The output here is 5. This is because the optimal strategy is to buy the stock on day 2, when the price is 1, and sell it on day 5, when the price is 6. The profit is calculated as 6 minus 1, which equals 5. It's important to note that buying at 7 and selling at 6 is invalid because you must buy before you sell. Now, in the second example, the input is prices equals 7, 6, 4, 3, 1. For the second example, the output is 0. Here, the prices are continuously decreasing, which means there is no opportunity to make a profit. Since no transaction can yield a positive result, the maximum profit is 0. Moving on to the third example, the input is prices equals 2, 4, 1. In this case, the output is 2. The best approach is to buy on day 1, when the price is 2, and sell on day 2, when the price is 4. The profit is 4 minus 2, which equals 2. These examples highlight how the solution should evaluate different scenarios to determine maximum profit. Now, let's explore the constraints and edge cases to better understand the problem's requirements. The constraints for this problem specify that the length of the prices array will be between 1 and 100,000, and each price will be a non-negative integer ranging from 0 to 10,000. It's crucial to consider edge cases when designing the solution. For instance, if the array contains only one element, no transactions can occur, so the output should be 0. Similarly, if all prices are the same, no profit can be made. When prices are strictly decreasing, like in prices equals 10, 9, 8, 7, the result is also 0. Additionally, the solution needs to handle the upper limit of 100,000 elements efficiently, which means it must run in O(n) time complexity. Keeping these constraints and edge cases in mind will help ensure your solution is both correct and optimized. To begin solving the problem, we can consider the brute force approach. The intuition here is quite straightforward. For every possible pair of days, we calculate the profit if we buy on the earlier day and sell on the later day. This means for each day I, we iterate through all subsequent days j and compute the profit as prices, j, prices, I. While this ensures we evaluate every possible buying and selling combination, it requires two nested loops, one for the buying day and one for the selling day. As a result, the time complexity of this approach is O(n squared, which makes it impractical for large input sizes. On the positive side, it's simple to implement, and it guarantees we'll find the maximum profit. However, due to its inefficiency, we need a better solution for larger datasets. Now, let's focus on the optimized approach, which uses a one-pass solution with minimum tracking. The key insight is that to maximize profit, we don't need to evaluate every pair of days explicitly. Instead, as we iterate through the prices, we keep track of two things: the minimum price encountered so far and the maximum profit we could achieve if we sold on that day. We start by initializing min_price to a very large value, like infinity, and max_profit to 0. For each price in the array, we update min_price to the smaller of the current price and the previously stored min_price. Then, we calculate the potential profit as the difference between the current price and the min_price. If this potential profit is greater than the current max_profit, we update max_profit. By the end of the loop, max_profit holds the maximum possible profit. This approach is efficient because it processes the array in a single pass, avoiding redundant calculations. It also handles edge cases naturally, such as when prices are non-increasing, by ensuring the calculated profit never drops below zero. The chosen strategy here is the optimized one-pass solution with minimum tracking, as it strikes the perfect balance between simplicity, efficiency, and clarity. With a time complexity of O(n), it is well suited for handling large input sizes, up to 10 to the power of 5 prices, without performance issues. The logic of dynamically tracking the minimum price and calculating potential profits is intuitive and easy to implement, making this approach clear and accessible. Additionally, its space complexity is O(1), meaning it operates with minimal memory usage. While the brute force method ensures correctness, its inefficiency makes it unsuitable for larger datasets. Other alternatives, like adapting Cadon's algorithm, introduce unnecessary complexity without adding significant value for this specific problem. By choosing the optimized approach, we ensure that our solution is both robust and efficient, handling all edge cases, such as arrays with fewer than 2 prices or non-increasing prices, to guarantee a correct and practical implementation. To solve the problem of finding the maximum profit from a single buy and sell transaction, we start by understanding the input and goal. The input is an array called prices, where each element represents the stock price on a specific day. Our objective is to find 2 days, I and j, such that we buy on day I and sell on day j, with j greater than I, maximizing the profit from this transaction. To approach this systematically, we initialize a variable max_profit to 0. This will keep track of the highest profit we've found so far. Then, we use a nested loop structure. The outer loop selects each potential by day, iterating from the first day up to the second to last day, since we need at least 1 day after the buy day to sell. This setup ensures we examine all possible starting points for our transactions. Now, for each buy day selected by the outer loop, we use an inner loop to explore all possible sell days that come after it. For each pair of days, I, j, where j greater than I, we calculate the profit using the formula prices, j, prices, I. If the result is greater than the current value of max_profit, we update max_profit to reflect this new maximum. After both loops finish iterating through all possible day pairs, the value of max_profit will hold the highest profit achievable. This approach, while straightforward and thorough, examines every combination of buy and sell days to ensure we don't miss any potential opportunities. However, it's important to note that this exhaustive search comes at the cost of efficiency, with a time complexity of O(n squared). This quadratic growth means that the runtime increases significantly as the array size grows, making it impractical for very large datasets. The space complexity, on the other hand, remains O(1), as no additional memory is used beyond the variables already defined. The brute force approach relies heavily on the structure of the input array and simple variable tracking. The input array prices is the sole data structure required, as it stores the stock prices for each day. Beyond this, we use the variable max_profit to keep track of the highest profit we've encountered during the iteration process. The key operations in this algorithm are straightforward but computationally intensive. First, we calculate the profit for every pair of days, I, j, using the formula prices, j, prices, I. This ensures we evaluate all possible buy and sell combinations. Then, we compare each calculated profit to the current max_profit. If the new profit is higher, we update max_profit to reflect this new value. Together, these operations form the core of the algorithm, systematically identifying the best possible transaction. To make this process more tangible, let's walk through an example with the input array prices equals 7, 1, 5, 3, 6, 4. We start by initializing max_profit to 0. On the first iteration, we choose I equals 0, meaning we buy on day 0 at a price of 7. The inner loop then examines each subsequent day as a potential sell day. Selling on day 1 at a price of 1 results in a profit of 1 is 7 equals -6, which is not valid, so we skip it. Similarly, selling on day 2 yields a profit of 5, 7 equals -2, which is also skipped. This process continues until all sell options for day 0 are exhausted. Next, we move to I equals 1, buying on day 1 at a price of 1. Here, the inner loop identifies a valid profit of 5 when selling on day 4 at a price of 6. This updates max underscore profit to 5. The algorithm completes by iterating through all remaining pairs, confirming that no higher profit exists. The final result is a max underscore profit of 5, which is returned as the solution. This Python implementation solves LeetCode problem number 121, best time to buy and sell stock using an efficient single-pass approach. The goal of the problem is to determine the maximum profit you can achieve by buying and selling a stock once, given an array of prices where each element represents the stock price on a certain day. The solution involves initializing two variables, min underscore price to track the lowest price encountered so far, and max underscore profit to track the highest profit achievable. Initially, min underscore price is set to infinity, a very high value, to ensure any price encountered will be lower, and max underscore profit is set to 0 since the minimum profit is 0 when no transactions are made. The algorithm iterates through each price and the prices list. At each step. 1. If the current price is lower than min underscore price, the code updates min underscore price to this new lower value. 2. Otherwise, it calculates the potential profit by subtracting min underscore price from the current price. If this profit exceeds the current max underscore profit, it updates max underscore profit with the new value. This approach ensures that we only track the minimum price and maximum profit in a single loop, making the algorithm highly efficient with a time complexity of O(n), where n is the number of days, or the length of the prices array. The space complexity is O(1), since we use only two variables for tracking and do not use any additional data structures. This solution handles all edge cases, such as when the input list is empty or contains only one price, by returning 0 as no transactions can be made in these scenarios. The code is concise and production-ready, ensuring clarity and correctness. This is the Java implementation of the best time to buy and sell stock problem, LeetCode number 121. The logic mirrors the Python solution, with type declarations and Java-specific constructs. The algorithm iterates through the prices array, maintaining the minimum price encountered so far and calculating the maximum profit possible at each step. Key differences from Python include type declarations, int instead of dynamic typing, and the use of integer.max_value to represent infinity. Let's start by analyzing the first example where the prices are 7, 1, 5, 3, 6, 4. Initially, we set min underscore price to infinity and max underscore profit to 0. On the first day, the price is 7. Since this is the first day, we compare 7 with min underscore price, which is currently infinity, and update min underscore price to 7. Since there's no prior day to calculate profit, we leave max underscore profit as 0. Now, after day 1, the state is min underscore price equals 7 and max underscore profit equals 0. Next, on the second day, the price is 1. We compare 1 with the current min underscore price, which is 7, and find that 1 is smaller. Therefore, we update min underscore price to 1. Again, since we are updating the minimum price, no profit is calculated yet. The current state is now min underscore price equals 1 and max underscore profit equals 0. On day 3, the price is 5. Here, we compare 5 with the current min underscore price, which is 1. Since 5 is greater than 1, the min underscore price remains unchanged. Next, we calculate the profit for this day as the difference between the current price and min underscore price, which is 5, 1 equals 4. We then update max underscore profit by taking the maximum of the previous max underscore profit, which is 0, and the calculated profit, resulting in a new max underscore profit of 4. The current state becomes min underscore price equals 1 and max underscore profit equals 4. On day 4, the price drops to 3. Comparing 3 with the current min underscore price of 1 shows that min underscore price remains unchanged. The profit for this day is calculated as 3, 1 equals 2. Since this is less than the current max underscore profit of 4, we don't update max underscore profit. The state remains min underscore price equals 1 and max underscore profit equals 4. On day 5, the price rises to 6. We compare 6 with the current min underscore price, which is 1. Since 6 is greater, the min underscore price remains unchanged. The profit is calculated as 6, 1 equals 5. This time, the profit is greater than the current max underscore profit of 4, so we update max underscore profit to 5. The current state is now min_price equals 1 and max_profit equals 5. On day 6, the price drops to 4. Comparing 4 with the current min_price of 1 shows no change in min_price. The profit for this day is 4, 1 equals 3, which is less than the current max_profit of 5, so max_profit remains unchanged. The final state after processing all prices is min_price equals 1 and max_profit equals 5. Therefore, the maximum profit for this example is 5. Now, let's examine a second example with prices 7, 6, 4, 3, 1. Initially, we set min_price to infinity and max_profit to 0. On the first day, the price is 7. We compare 7 with min_price, which is infinity, and update min_price to 7. Since this is the first day, there is no profit calculation, leaving max_profit at 0. The state is now min_price equals 7 and max_profit equals 0. On the second day, the price drops to 6. We compare 6 with the current min_price of 7 and update min_price to 6. Again, no profit is calculated at this point, so the state remains min_price equals 6 and max_profit equals 0. On day 3, the price drops further to 4. Comparing 4 with the current min_price of 6, we update min_price to 4. Since no profit is possible yet, max_profit remains 0. The state becomes min_price equals 4 and max_profit equals 0. On day 4, the price drops again to 3. We compare 3 with the current min_price of 4 and update min_price to 3. As before, no profit is calculated, so max_profit stays at 0. Finally, on day 5, the price drops to 1. We compare 1 with the current min_price of 3 and update min_price to 1. Again, no profit is possible, leaving max_profit at 0. The final state is min_price equals 1 and max_profit equals 0. Since no profit can be made in this example, the output is 0. In the third example, the prices are 1, 2, 3, 4, 5. Initially, min_price is set to infinity and max_profit to 0. On the first day, the price is 1. We compare 1 with min_price, which is infinity, and update min_price to 1. No profit is calculated since this is the first day, leaving the state as min_price equals 1 and max_profit equals 0. On the second day, the price rises to 2. Comparing 2 with the current min_price of 1, we find that min_price remains unchanged. The profit is calculated as 2, 1 equals 1. We update max_profit to the maximum of the previous max_profit, 0, and the calculated profit, resulting in max_profit equals 1. The current state becomes min_price equals 1 and max_profit equals 1. On day 3, the price rises to 3. Comparing 3 with the current min_price of 1, we see no change in min_price. The profit is calculated as 3, 1 equals 2. Since this is greater than the current max_profit of 1, we update max_profit to 2. The state becomes min_price equals 1 and max_profit equals 2. On day 4, the price increases to 4. Again, min_price remains 1, and the profit is calculated as 4, 1 equals 3. This is greater than the current max_profit of 2, so we update max_profit to 3. The state is now min_price equals 1 and max_profit equals 3. On day 5, the price rises further to 5. The min_price remains 1, and the profit is calculated as 5, 1 equals 4. Since this is greater than the current max_profit of 3, we update max_profit to 4. The final state is min_price equals 1 and max_profit equals 4. Therefore, the maximum profit for this example is 4. In summary, across all examples, the algorithm efficiently tracks the minimum price and calculates the maximum profit in a single pass through the prices list. With a time complexity of O(n) and a space complexity of O(1), this approach ensures that the best possible profit is determined by comparing each price with the minimum price seen so far and updating the maximum profit as needed. The time complexity of this solution is O(n), where n represents the number of elements in the input list, prices. This is because the algorithm processes the list in a single pass using one for loop. For each element in the list, we perform a constant amount of work. Specifically, we compare the current price with the variable min_price, which takes constant time, O(1). If the condition to update the maximum profit is met, we calculate the profit and update max_profit, and both of these operations are also O(1). Since we only iterate through the list once, and every operation within each iteration is constant in time, the total time complexity becomes proportional to the number of elements in the list, resulting in O(n). This holds true for all cases, whether the input is best, average, or worst, because the algorithm consistently processes each price exactly once. Therefore, the time complexity is O(n), regardless of the input's pattern. The space complexity of this solution is O(1), meaning the memory usage does not grow with the size of the input list. This is because the algorithm only uses two scalar variables, min_price to keep track of the smallest price encountered so far, and max_profit to store the maximum profit calculated. Scalar variables require constant space, regardless of how large the input list is. Additionally, no additional data structures like arrays or hash maps are used, and the input list itself is not modified, so no extra memory is allocated. Since the memory usage remains constant and does not depend on the size of the input, the space complexity is O(1). To better understand the efficiency of this solution, let's compare it with the brute force approach. In a brute force method, we would examine all possible pairs of days, I, j, where I is less than j, and calculate the profit for each pair. This would involve two nested loops, the outer loop iterating over each day I, which is O(n), and the inner loop iterating over all subsequent days j, which is O(n_i). Combining these loops results in a time complexity of O(n²) in the worst case. However, even with this inefficiency, the space complexity of the brute force approach remains O(1), as no extra storage is used. In contrast, the optimized solution avoids nested loops entirely by maintaining a running minimum price and calculating the profit in a single pass. This reduces the time complexity from O(n² to O(n), a significant improvement for large inputs. The space complexity remains O(1), consistent with the brute force method. This makes the optimized solution far more efficient for handling large datasets. To solidify our understanding, let's look at a mathematical breakdown of the big O analysis. First, the single for loop iterates through the input list exactly once. Each iteration involves a constant amount of work, such as comparisons and updates, all of which take O(1) time. Therefore, the total time for the loop is the number of iterations, n, multiplied by O(1) operations per iteration, yielding a total time complexity of O(n). Second, there are no nested loops or recursive calls in the algorithm, so no additional multiplicative factors are introduced. Lastly, in terms of space, the algorithm only uses two scalar variables, min_price and max_profit, regardless of the size of the input list. Since these variables require constant memory, the space complexity is O(1). Combining these factors, the solution achieves an optimal balance of O(n), time complexity, and O(1), space complexity, making it both time efficient and memory efficient. When solving this problem, there are several common mistakes to watch out for. First, be cautious with edge cases. If the input array is empty or contains only one element, there are no valid by-cell pairs, so the function should return 0 or another default value. Another pitfall is confusing the by and cell days. Remember, the cell day must always come after the by day, so ensure your solution maintains the constraint that the index of the cell day is greater than that of the by day. Additionally, avoid using nested loops unnecessarily. While a brute force approach works for small input sizes, it becomes highly inefficient for larger arrays, so optimizing to a one-pass solution is critical. Also, if you're working in a competitive programming setting, be careful to reset variables between test cases. Forgetting to do this can lead to incorrect results. Finally, watch out for off-by-one errors, such as iterating past valid indices or accessing elements outside the array bounds. These small mistakes can lead to runtime errors, so always double-check your loops and conditionals. Now, when approaching this problem in an interview, it's important to understand the scope of the problem. Determine whether you're solving for a single buy-sell pair or if multiple transactions are allowed, as this will dictate the algorithm you use. For the basic problem, leverage the greedy approach. By keeping track of the minimum price encountered so far and the maximum profit at each step, you can solve the problem in O(n) time with O(1) space. It's also important to test your solution with diverse input cases, such as arrays with prices that only increase, only decrease, or alternate between highs and lows. These tests help ensure your solution handles edge cases effectively. During the interview, take the time to explain the trade-offs between different approaches. For example, you can highlight why a brute force solution with O(n) squared complexity is inefficient and how the greedy O(n) method works better. This demonstrates not only your ability to code but also your analytical thinking and problem-solving skills. To deepen your understanding of this problem, it helps to explore related problems that build on the same concepts. Start with LeetCode 121, the basic version, to master the fundamentals. Then, move on to LeetCode 122, which introduces multiple transactions and requires a different approach. Next, tackle LeetCode 123, where you solve for at most 2 transactions, and LeetCode 188, which extends this to k transactions, requiring dynamic programming techniques. Finally, explore LeetCode 309, which adds the complexity of cooldown periods, pushing you to incorporate additional constraints. These related problems provide a progression of difficulty and help you develop a strong foundation for solving variations of the stock trading problem. There are several approaches to solving this problem, each with its own trade-offs. The brute force method, which has O(n) squared time complexity, involves checking all possible buy-sell pairs. While inefficient for larger arrays, this approach is a good starting point to understand the problem. A more efficient solution is the greedy single-pass algorithm with O(n) time complexity. By tracking the minimum price so far and calculating the maximum profit at each step, you can solve the problem efficiently. However, this method is limited to scenarios with only one transaction. For more advanced variations, like handling multiple transactions or other constraints, dynamic programming is the preferred approach. Although it introduces additional complexity and space requirements, dynamic programming can handle problems with multiple transactions or specific rules, such as cooldown periods or transaction limits. Choosing the right approach depends on the specific problem requirements and constraints you're dealing with. That wraps up our tutorial on the best time to buy and sell stock problem. We explored how to maximize profit using an optimal single-pass solution. Key takeaways include the importance of maintaining state variables and recognizing patterns for greedy algorithms. Thanks for watching. Don't forget to like, share, and subscribe for more problem-solving tips. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!